All right, in this podcast, we're going to talk about the buffer region, which I mentioned when we were looking at titration. Okay, so let's actually really talk about this buffer region. So we know that the buffer region is located in this area. The buffer region, it's going to occur when you have the reaction of a weak acid with a strong base or a weak base with a strong acid. Both of them will give you a buffer region. The thing about buffer regions is that they resist a change in pH. So you keep adding base to them, and the pH is just not changing very much. So the thing that's kind of interesting about them is from 10% to 90% of the base that you need to reach equivalence, adding that 10% to that 90% will only give you about a 1.5 change in your pH value. And we can also determine Ka by looking at our buffer region. Okay, so chemically, how does this actually work? Okay, so we know that we already have a weak acid equilibrium going on where we've got the weak acid producing some H plus and the conjugate base. Okay, now we add the NaOH. NaOH is a strong base, so it's going to be completely dissolved, and so you're going to get all these OH minuses. Those OH minuses grab the H pluses out of a solution and make water. Now, because that top equation, our weak acid equation, has H in it, as we are reacting the H pluses, they're being removed from solution. So as they're being removed, the equilibrium is continually shifting more and more and more to the right. So we remove some H plus values, some H plus ions in order to raise the pH to get it to neutral, and in turn the equilibrium just continues shifting towards the right and making more H pluses, which is why you have such a slow change in the pH, because every time you remove an H plus, it seems like the system just produces another one for you. Okay, so to calculate the pH in the buffer region, we have to use something called the Henderson-Hasselbach equation. The Henderson-Hasselbach equation tells us that pH is equal to the pKa plus the log of the conjugate base over the acid. So we want the concentration of the conjugate base over the acid, and then we're going to log that, add it to our pKa, and that'll be our pH. All right, so here is an example of that. So in this one, we want to know what the pH is going to be when we have this 25 mils of our acetic mixed with 7.5 mils of the NaOH. Okay, so first thing that I like to do is I like to just have the reaction there in front of me so that I actually know what I'm looking at. So we know that it's going to make our salt and our water. Okay, so first thing I need to do is I need to figure out how much of my acid is actually going to get reacted, right? So in order to do that, I need to know the concentration, or not the concentration, I need to know the moles of my acid. So I'm going to do molarity equals moles over liters. So I got my 0.1 equals X over 0.025, cross multiply, and I get 0.0025 moles of my acid. All right, now I need to do the same thing for my base. So my base, I've got 7.5 mils, and your teacher's goofy and forgot to put the concentration of NaOH, but it was supposed to be 0.1. So I've got a 0.1 molar NaOH solution, so now I need to find the number of moles of NaOH that I have. So I do the same equation, and I've got my concentration as 0.1, my moles is X, and then 0.0075 is going to be my volume. So that means that I have 0.00075 moles of my NaOH. Okay, so clearly NaOH is the limiting reactant here. So I'm going to use all of it, end up with 0 NaOH, and then I am going to convert some of the acid into the salt, right? So if I subtract these two values right here, I'm going to have oops, I don't know why I put a line there. Okay, I'm going to have 0.00175 moles of my excess acid, okay? And now for over here, this started at 0, right? And then it made that many moles. So I've got this many moles of my conjugate base. This one is my conjugate base, so we'll just call it A minus, and this one over here is my acid. Okay, so that's great. I got the moles. Now I've got to get their concentration. So I need to divide them by our new total volume. So 7.5 plus 25 gives us 32.5, and then convert that to liters so that we can get back to concentration, and we will get our new molarity values. So for this one, I got 0.0538 molar, and that's your acid. And then for my conjugate base, I got 0.0231 molar. All right, now all I got to do now is just plug it in. So I got pH equals, okay, now I needed to do the pKa of my Ka. So if you negative log this number, you get 4.74 plus the log of my conjugate base over my acid. All right, so now it's just a math problem. Plug it in. This guy right here ends up being negative 0.367. So then 4.74 minus 0.367, so my final pH at that point is 4.343. Okay, we can also find pKa from a titration curve. So at half equivalence, we know that the pH is equal to the pKa. Okay, so remember back when we talked about weak acid, strong base solutions, or actually any kind of titration. At half equivalence is when you have half of the acid converted into the conjugate base. So at that point, the concentration of your acid is equivalent to your concentration of conjugate base. Now, if you had your Henderson-Hasselbach equation there, and you were going to plug these in, it would be the log of 1, right? Because they're the same. Guess what? The log of 1 is 0. So at that point, pH is equal to pKa. Okay, so if you can find your equivalence, go to half volume, trace it up. That point right there, whatever the pH is, that is our pKa. And then, of course, you can back calculate from pKa to the Ka. Okay, so how do we actually apply that knowledge? So we apply that knowledge because we can actually determine acid strength from just looking at curves. Okay, so we know that equivalence was reached at 20 mils, so 10 mils is going to be our half equivalence. So we're looking at this basically on our curves. So we've got pKa values of 4, about 6, and about 8. So the question is, which one is the weakest acid? Now, if you'll remember the relationship between pKa's and Ka's, the more negative the Ka, the stronger or the higher, larger your Ka value is. So the weakest acid on here is definitely going to be acid C. Okay, which acid would have a Ka of 10 to the negative 4th? Okay, so if you negative log 10 to the negative 4th, you would get 4. So basically it wants to know which acid has a pKa of 4, and that would clearly be acid A. Last question, what is the concentration of all of the acids if 10 mils of each of the acids were titrated with 0.1 molar NaOH? Well, these are all monoprotic acids, so we can just simply use M1V1 equals M2V2. So for my acid, I don't know my concentration, but I do know that I used 10 mils of them. And for my base, I know that the concentration is 0.1, and it took me 20 mils to get to equivalence for each of these. And then divide, and you get that your concentration of each acid is 0.2 molar. All right, so let's talk about qualitatively what can we understand from the buffer region. Okay, so we know, so here is equivalence, right? So equivalence is about 25. So about 12.5 is going to be our half equivalence. So at half equivalence, we know that the HA is equivalent to the A minus. So the acid is equal to the conjugate base. Okay? Now before half equivalence, you have more acid than you do base. Okay? And then once you get past half equivalence, but before equivalence, you have more of the conjugate acid than you do the acid. So this can help us determine the dominant species at a certain point in the buffer region. Okay, so let's look at some examples. Okay, so on this titration curve over here, we want to label where the base concentration is greater than the conjugate acid. All right, so they flipped it for us. This is a weak base with a strong acid titrant. So we're starting in the basic pH range and then going to acidic. So our buffer region is right here, right? There's our buffer region. So it wants to know where the base is greater than the conjugate acid. So in a weak base, strong acid, you are looking for your base to conjugate base ratio, okay? So this is what we're looking for here, okay? So anything before half equivalence is going to be basic. So basically looking at that region right there. That's where you're going to have more of the base than the conjugate acid. Okay, the next question says if this base was ammonia, NH3, which of the following representations of the species of NH3 and NH4 plus are present at a pH of 10.4? And it tells us that our pKb is 9.26. Okay, so I'm going to erase for us real quick so that we can have a nice little discussion here. So the pKb is 9.26, so that's, roughly right there in that area. Okay, now we want to know what it looks like at a pH of 10.4, so we're up towards right here, okay? All right, so we definitely know that because we're before the equivalence point, we should have more of the weak base than we should have of the conjugate acid. Okay? All right. So definitely need to make sure we have more NH3 than we do NH4 plus. Okay. So let's start looking at our pictures down here. So the NH4 pluses are all have little plus signs and they have 4 little things hanging off, right? Okay. So I've got 1, 2, 3, 4, 5. So 5 of the conjugate base, conjugate acid, and then I only have 3 of my base. Okay, so that definitely is not where we're at, right? Because we just said that we definitely are going to have more of the base than we are of the acid. Okay, so definitely that one's out. All right, this one here, we've got 1, 2, 3 of our conjugate base, and we have 1, 2, 3, 4, 5. We have 5 of the base. Okay, so this is looking a little better because at least we have more base than we do conjugate acid. Okay, so maybe on B. All right, let's keep going. C, we've got 1, 2, 3, 4. But we got 4 of the conjugate acid, and then 1, 2, 3, 4 of the base. So this is half equivalence, folks. This is half equivalence. So that's definitely not it. All right, and then next one, we have 1 of our conjugate acid, and then 1, 2, 3, 4, 5, 6, 7 of our base. So both B and D, we have more. Now we got to figure out which is which. So we can actually just plug this in over here and just try some stuff. So pH equals pKb plus the log of your conjugate acid over your base. Okay, so even though you might not think of these things right here as concentrations, we can use them that way. Okay, so over here, and we know our pKb is 9.26, and then if I look at this one, B, and we do the log of 3 of our conjugate acid over 5 of our base, we get 0.22. Well, you guys obviously realize that 9.26 plus 0.22 is not going to give you 10.4. Okay, now let's check D. So D is going to be the log of 1 of our conjugate acids over 7 of our base. And if we log that one, we get 0.84. So 9.26 plus 0.84 gives you 10.4. So it's got to be this one, because this is the one that gives you the correct concentration. All right. This one wants us to look at the particulate diagrams, okay? So particulate diagrams are a big thing on the AP exam nowadays. So we have a titration of this weak acid with a strong base, and we want to know what it looks like at half equivalence. So again, y'all know me. First thing I'm going to do is write the equation. It just helps me visualize what's going on here. Okay. So that's what I got right there. Okay, that's what's happening. Now, at half equivalence, I know that the concentration of my acid should be equivalent to the concentration of my conjugate base. Okay, I should have absolutely no dissociated H plus and OH minuses, okay? We shouldn't have any extra of those floating around in solution, okay? So we definitely know that our NH2O is going to be bound. And then because we got the lithium attached here, we're actually going to end up with some lithiums and some of the conjugate base there. So all of these should be equivalent. And also, we should have the same concentration of our water. We should have made the same amount of water as we did our salt. Okay, so now we want to pick the picture that all these are equivalent. So HNO₂ is going to be the circle with the little colored in circle. Li plus is going to be the colored in triangle. Okay, NO2 minus not bound is just going to be the open circle. And then HOH is going to be the box with the colored in dark circle. So we just want to find something where all of these are equivalent. Okay, so if we look at A, first off, it's showing that is bound. Okay, and then I have no bound acids. So that is not good. Okay, so that's not it. All right, B. First off, notice that I have a bunch of unbound H's here. I also have some bound acids, which is good. And then I have a Li and an OH bound. That's weird because LiOH, number one, is a strong base, so it should completely dissociate it. It shouldn't be bound. And number 2, we just used all of it to neutralize half the acid. So that can't be it. All right, C. All right, we got our waters, so that's good. There's our waters. Okay, we got some unbound Li, and then we got some of our salt. Our problem here is, where is the acid, the bound acid? There's no bound acid, so that can't be it. All right, and then this one, you see I have 2 of my conjugate base, and then I have 2 of my lithium ions. I have 2 of my acids bound, and then I have 2 waters. So D is definitely the correct answer here. And last part, we are to assume that we have 5 molecules of nitrous acid, and we have 7 molecules of lithium hydroxide, and we need to draw a particulate representation. Okay, so first off, understand that now your acid is your limiting reactant. So we're going to completely react all of the HNO₂. So there's not going to be any of this left, okay? And because we have a 1-to-1 ratio, we subtract out that 5 molecules. We will have 2 molecules of LiOH that are excess. Because we had the 5 of our acid, we made the 5 of our conjugate base, and we also made 5 of our waters. Okay, so now it's just the whole point of drawing them. All right, so Li and OH. This is a strong base. So when I draw my Li and my OH, I need to make sure that they are not stuck together, because conjugate bases, as you know, completely dissociate. So there's my 2 Li's, and then my OH's are my boxes. Okay, so there's my OH and my Li. All right, now over here on this other side, my salt is LiNO₂. Again, because Li is something that's always soluble, I've got 5 more of those suckers floating around over here by themselves, so you need to draw 5 of those. Okay, let's see how many that for me. 1, 2, 3, 4. Okay, and 5. Okay, so there's all my Li's. Now I need my NO2 minuses. I had 5 of those, so 1, 2, 3, 4, 5. All right, and then I got 5 of my HOH's. So HOH and HOH and HOH and HOH and HOH. And bam, there you go.